you by Thesis123.com. I learn and teach online.
Here's the next question, number 45. The voltage Vs across and the current Is through a semiconductor switch during a turn-on transition are shown in the figure. The energy dissipated during the turn-on transition in millijoule is dash. Okay, so here we have been given a graph with Vs and Vi for the switch. So we notice here that during the turn-on transition, here this time here T1 and T2, there is a change in both voltage and current, and there is a linear change. The voltage linearly decreases while the current linearly increases. So here's something that you would have to know. For a turn-on transition, the switch is initially off and then turned on. Now because the voltage and current go through a gradual change, it is called transition. For an ideal switch, there is an instantaneous change. An instantaneous change means that the voltage, as soon as the switch is turned on, the voltage immediately drops down to 0. There is a vertical decrease, an immediate decrease. There is no change here. While for the current, there would be an immediate increase or just a immediate instantaneous increase. There's a vertical line, there is no gradual increase. So this is a practical case where we see a gradual decrease in voltage and a gradual increase in current. So since we are to find out the energy dissipated, let's write down the general formula for energy: power multiplied by time. Now because this is not an ideal switch and we don't have a fixed value for power, that's the case over here. Since we don't have a fixed value for voltage and we don't have a fixed value for current and they are changing, we cannot consider this equation. Rather, we consider the integration during the time period for power dt. So the time period is T1 and T2. So it has been divided into two parts. So we will divide this into two parts as well. E is equal to, during the period T1, power dt, plus during the period T2, power dt. Now the formula for power in terms of voltage and current can be written as V of t, I of t dt plus T2 V of t, I of t dt, since power is Vi. So these are the basics. We always take the basics and we build on it based on the situation given to us. So here we have our energy equation. We have for time period T1 for 1 microsecond and the time period T2 for again 1 microsecond. Let me just grab another sheet of paper here and I'll work out the rest. Okay, so our energy equation is T1 V of t, I of t dt plus T2 V of t, I of t dt. Now according to the waveform given to us, we see that here during the period T1 the voltage is constant at 600 and during the period T2 it is gradually decreasing. So now for the first portion here I'll just write that down. Integral of, this is during the first period, Vt is 600 but It is increasing during this period of T1. Now since this is a linear line, we don't have an equation for it. We need an equation for it. So let's write that as It for now, plus integral T2. Now for the second period of time, we have a change in voltage, which is a linear line, and we don't have the equation for this. So let's just write that as V of t times I of t. Now I of t is a constant line here, and if we notice, it is at 100 amps. This portion is 100 amps. So we have our values. This is 100 dt. Now the next step is to figure out what to plug in for I of t and v of t. Since this is integration, I'm sure you're quite familiar with the fact that we can find out the integral by calculating the area under the curve. So here we consider this triangle and find out the area under the linear line, and in case of the current we find out the area of this portion here to determine what I of t is. Okay, so we know the formula for area of a triangle, right? Half into width into length, width into height in this case. So we have here width and we have here as the height. So the width is 1 microsecond for both triangles. The height is 600 for the voltage triangle and 150 for the current triangle. So this portion is 100 and the rest is 50. So that's a total of 150. So let me just put that down here. We have 600 into now the current triangle. The current triangle, half into width 1 into 10 power minus 6 into height 150. So this is our first. The second part is half 1 into 10 power minus 6 times the height is 600 for the voltage triangle into we have 100 over here. Now if we solve this portion, so that would be 300, here that's 300 as well. Give you a moment and you can actually solve it. You should get a value of, let me just get the calculator here, 75,000 10 power minus 6 joule should be the result of that entire equation, 75,000 into 10 power minus 6. Now 10 power minus 6 is micro. So if you solve this expression here, you will get 75 millijoules. That's because the question asks in terms of millijoules. Okay, so 10 power minus 6. Here we have 75,000. If we write this as 75 into 10 power 3, we will get that in terms of 75 millijoules. So here is our final answer. 75 is the final answer. I hope this has helped.
Thank you for watching this video. For future videos, please click here to subscribe YouTube channel. Visit our site thesis123.com for free student project or research ideas and online training. Follow us Facebook, Twitter, Google+ and Pinterest.